Exploration programs like these have vastly increased our knowledge of space. But what about other important regions, such as the middle and upper atmosphere? These regions are too low for long-term data collection by rockets and shuttles, and too high for conventional aircraft to reach. Qualified people have successfully conducted experiments within these regions of the atmosphere. The tools they use are versatile and inexpensive, quietly waiting to rise to the occasion. In this era of high-tech experimentation, a simple balloon platform can rise to an altitude that's a near-space environment and remain constant for a longer period than the more sophisticated rockets and shuttles. The Air Force has been a major participant in balloon research. Although our name and the location of our organization has changed over the years, today as the Phillips Laboratory, we continue to manage balloon programs for the Department of Defense. Balloons have played a significant role in research, development, and testing since 1947. The environment around us has always been intriguing. Scientists during the 50s were curious, for little was known of weather conditions above 30,000 feet. With a balloon program called Moby Dick, our laboratory had a unique opportunity to measure wind fields to specify the new jet engine flight environment and develop and test various types of balloons. The data and the experience gained from 640 Moby Dick flights became the most advanced information available on wind velocities up to 100,000 feet, and what specific balloon materials and fabrication methods were reliable. A major environmental issue today is air pollution. Numerous studies and tests in progress deal with improving the air we breathe. But this issue is not new. Clean air was also important during the 50s. At that time, our laboratory worked with the Department of Energy on a program called Project Ashcan. This balloon platform carries samplers and sensors through the upper atmosphere to collect data on nuclear and naturally produced debris. Ashcan was the first to gather and measure debris in the stratosphere from the eruption of El Chicon in 1982. Periodically, Ashcan still flies, and the data that has been collected and analyzed will move us closer to a clean environment. In 1962, our laboratory explored the field of astronomical phenomena. Project Stargazer was the first balloon flight of its kind, a pressurized gondola designed as an astronomical laboratory with a two-man crew. The 12-inch revolving telescope was operated by the crew. The 4,800-pound Stargazer was launched on December 13, 1962. It reached an altitude of 81,500 feet. After 18 hours aloft, the gondola and its crew were successfully recovered. Through the years, free flight balloon operations have coincided with tethered balloon operations. These tethered systems began as a possible solution for communications relay systems during the Vietnam operations, and as development and test support for lunar exploration. The Surveyor was suspended 1,500 feet up beneath an open parachute. The Vernier rockets fired at 800 feet. The numerous drops conducted to test the Surveyor's retrofire descent and impact capabilities were performed from a position-stabilized tethered balloon. Unlike a tower, this tri-tethered platform provided unobstructed viewing during the tests. The parachute recovery system assisted in simulating a lunar landing. tethered balloons also demonstrated the feasibility of using a small balloon to support a special antenna as an emergency replacement for disabled antenna towers. We've also used interconnected but widely separated tethered balloons to raise and lower a net of cable to collect effluents. These tests were to determine the extent of carbon fiber burns from a simulated aircraft crash. When the United States was gearing up for planetary missions, the Air Force balloon operations played an important role. Our laboratory supported the development of decelerators and parachute systems for the Voyager and Viking programs. In 1966, we launched two of the largest balloons ever fabricated. Each balloon measured 26 million cubic feet in volume, twice that of any previous balloon launched. The vertical length was 815 feet, 260 feet higher than the Washington Monument. The diameter at altitude was 410 feet. The rocket-powered capsule released the parachute system at a speed that, when combined with atmospheric density, simulated the environment of Mars. During July and August 1972, our laboratory supported the NASA Viking program. Again, this involved a balloon platform, a rocket-powered capsule, and a parachute system. Our laboratory designed the balloon system and developed the electronic equipment for command and control functions. This balloon carried a 6,000-pound payload to 120,000 feet. Data from 4 successful balloon flights pinpointed the design and fabrication required for the Viking parachute system. In 1982, our free flight balloon operations became part of the Galileo to Jupiter program. Again, our responsibility was to test and verify the proper functioning of the parachute and separation systems. A prototype Galileo probe was raised 97,000 feet by a free balloon. The probe free fell to 57,000 feet. Ballast was released and the drogue chute deployed. The Galileo landing was a success. The Balloon Altitude Mosaic Measurements Program, or BAM, was active from 1978 through 1984. This experiment was to measure infrared Earth background signatures, such as solar glint from lakes, rivers, oceans, and snowfields. These signatures, or clutter, are what infrared surveillance sensors have to be able to identify and differentiate from enemy targets. The data obtained from these tests assist the Air Force in the design of surveillance sensors. A series of atmospheric balloon LiDAR experiments, or ABLE, has for the last 5 years tested the feasibility of using LiDAR as a global wind sounder. Wind data are derived by sensing density layers in the atmosphere. The ABLE experiment was successfully flown to 75,000 feet. A balloon's ability to withstand harsh environments was tested and verified in 1988 with GRAD, the Gamma Ray Advanced Detector Program. The Antarctic was the site of the experiment. The balloon floated at 115,000 feet for nearly 3 days. This environment near the magnetic pole exposed new gamma-ray detector materials and software methods to gamma radiation equivalent to that of space. Shields designed to reduce radiation noise and improve signal detection sensitivity were also tested. An additional bonus during the test was the chance to observe a supernova, the first since 1604. The payload was recovered 900 miles from the launch site with the assistance of the Antarctic Naval Support Force. Despite a power supply failure during the flight, 24 hours of data were acquired and the mission was deemed a success. Auroras, radiation, and background clutter all affect how efficiently optical sensors detect and track targets. Phillips Laboratory has been studying this subject for some time with the intention of enhancing Air Force surveillance and tracking capabilities. The Stratospheric Cryogenic Interferometer Balloon Experiment, or SCRIBE, measures emissions of infrared atmospheric spectral signatures within the stratosphere. A pointing mirror in front of the coolable telescope is used to make limb measurements. SCRIBE was launched from Holloman Air Force Base, New Mexico. The balloon reached a float altitude of about 33 kilometers. Approximately 6 hours of continuous measurements were recorded. This data will provide important information to be used to understand atmospheric transmission and radiance properties. During a span of 45 years, our laboratory has used this simple, versatile, inexpensive tool to learn more about the atmosphere. Our extensive background in balloon research, development, and testing qualifies our people at Phillips Laboratory as experts in the field. With our corporate knowledge in balloon research, we can reduce red tape and streamline your mission support. The Phillips Laboratory is committed to minimizing your risks, reducing your costs, and achieving success. We accomplish the mission objectives with proven methods, proven tools, and proven people.